Let's solve Unit 8 Theory of Computation and Compilers questions. Which of the following is true about the pumping lemma for regular language? When we say it's a pumping lemma for regular language, it applies to all context-free languages will be ruled out because there is a pumping lemma for context-free languages. Here for regular language you will be splitting the string into 3 strings, but in pumping lemma for CFL you have to split the string as 5 strings. And when this is a pumping lemma for regular language, definitely it will not apply to recursively enumerable languages. So we can even rule out option 4. Now it's between option 1 and 2. The pumping lemma states that for any regular language L, any regular language means it applies to all regular languages. Based on this particular statement, we can mark option number 1 to be the right answer. Now let's see the pumping lemma definition. There exists a constant P, which is the pumping length, such that any string S in L with a length of at least P can be divided into 3 parts. S is equal to X, Y, Z, satisfying the following conditions. So here the division is into 3 parts. But in CFL pumping lemma, you will be dividing it into 5 parts. So that is the difference there, and the conditions will also change based on those parts. For each I is greater than or equal to 0, X, Y power I, Z is in L. So when I is equal to 0, even when the Y part of the string is missing, X, Z should be there in the language. Length of Y is greater than 0. This states that the string Y should not be empty. The length of XY should be less than or equal to P. This P is nothing but the pumping length. So if all these 3 conditions are satisfied, then we can say that language is regular language. Whenever you take any language, there will be finite language and infinite language. In regular language, we say finite when we are able to produce all the strings of the language. Based on all the strings, we can say whether one string is existing in the language or not. But what about infinite regular languages? We will not know all the strings that belong to the language. Pumping lemma is actually used to check whether a language is regular or not in the case of infinite languages only. The application is mainly done for infinite regular languages. There are books which suggest that pumping lemma for regular language can be applied only to infinite language, because in finite cases we need not use pumping lemma is what they say. Next question. Which of the following represents the output of the transition function? Based on the option, you can understand it is a power n, b power n string. And usually we use push down automata to implement this particular string. Now we have to find what mission is this. This is actually Turing mission. When we have a transition del current state comma current symbol being read. So there are 2 parameters in del here. What happens in the transition is next state, symbol to be written, direction to move the tape head is given. In push down automata you have stack operation. But here when you have something called direction to move the tape head, you should understand that Turing mission is used here. So let's look at the option now. L is equal to a power n, b power n. They have given 4 conditions. The first condition is n is greater than or equal to 0, which means the n value will be starting from 0 and it goes on. What about the second option? They have given n greater than or equal to 1. So n value will be starting from 1 and it goes on. What about the third option? N greater than 0. This is also having the same set of values similar to option 2. What about fourth option? N greater than 1. Here the starting value of n will be from 2. It will not include 0 and 1. So basically we have to see when n is equal to 0, what happens? You will have empty string. Do you have any transition which has empty string operation? You have the initial state as Q0 here and the final state as QF. And here is something, a symbol like square. What is this square called? It's actually the blank symbol. Whenever you have a Turing machine, a blank will be denoted as the last character to say that you have reached the end of the string. That is, all the input characters or all the input symbols have been processed and you have come to the end. That is where we make use of blank to say that you have reached the end of the process. So from Q0, do we have any transition to process empty string? We have only one transition function Q0 comma A. So except for input A, we don't have any other transition starting with Q0 here. And similarly, we have something called Q0 comma Y. So Y is a part of the process. We will see that later. There is no transition that will process empty string. So we can rule out option 1 even before starting the work. Now let's take n is equal to 1. When n is equal to 1, we will have a power 1 b power 1 which is equal to ab. When n is equal to 2, a square and b square which can be represented as bb. So let's start with the first transition. So let's take this one. Del q0 comma a is equal to q1 comma x comma r. This indicates that the machine starts with an a, marks it as x and moves to the right, transitioning to state q1. Initially this is in q0 state along with the blank symbol. Now this a is marked as x. And what is the current state now? It is q1. So now it will be x, b along with blank. Where is the tape head moving now? To the right direction. Here is the tape head now. How do you read this particular transition? You have to read this as q1 comma b. So go for q1 comma b. It is here. What happens in q1 comma b? This marks the first b it encounters, moves to the left and transitions to state q2. So this b is now changed as y as we see here. It is the symbol to be written. So we are marking the first b as y and then we are moving to state q2. So now we will have q2 and the direction of head movement will be left. So we have x here. Now we are moving to this x. What is the next transition that we have to check? q2 comma x. Where is q2 comma x? It is here. What is the transition telling? You have to go to state q0. You are not marking anything there. X is staying as it is. So we are moving to state q0 here. And then we are moving to right means we are in y. So do we have any transition q0 comma y? We have here. This q2 comma x returns the machine to state q0, continuing the process until all a's and b's are matched. What about q0 comma y? From here, transitions indicate the machine is moving towards the final state after all a's and b's have been processed. Now what we have to do is, we have to go to q3 state. There is no marking of symbol, it is already y. And it is asking us to move towards right. So if you move towards right, what symbol is here? It is the blank symbol. So now we are moving to this particular blank symbol. What is the new transition now? q3 comma blank symbol. Do we have any transition here? Yes. q3 comma blank symbol will say you have reached the final state. So once you reach the final state, it means the string is accepted and you can understand the process has been successfully completed. When n is equal to 1, the language has the string AB and this is successfully processed by the Turing machine. Now let's take the next string. Where n is equal to 2, we will have AABB. So initially we will start with Q0. What is Q0 comma A? We are moving to q1, marking this a to be x and we are moving to the right. So here we are changing this as q1, we are marking this as x and we are moving to the next a. This is the right movement. Do we have any transition q1 comma a? Yes, we have. Let's take this particular transition. This allows the machine to continue reading as while moving to the right. So when you have other A's, it will just keep moving right. For first A, it will change the first B. And for the second A, it will change the second B. When you are taking one A for one B, what you can understand is you can check number of A's are equal to number of B's. When A is greater than B or when B is greater than A, there will be a problem in this particular matching. So based on that, we can understand that the string is not present in the language. So now we are in this particular transition Q1 comma A. What is happening here? You are still in Q1 but you are just moving to the right. So now we will just move to the right. We are in B. What about Q1 comma B? Q1 comma B we have already seen here. We are going to state Q2 marking it as Y. So we have X here, A here. This is changed as Y and the movement of the head will be towards the left. Now we are in state Q2. Do we have transition for Q2 comma A? Yes, we have here. Q2 comma A will be Q2 comma A along with left direction. So there is no change in the state. There is no marking but you are just moving to this particular X. So now the transition will be Q2 comma X. Do we have Q2 comma X? Yes, we have already seen that. We are moving to state Q0 and we are moving towards the right. So here we are moving to state Q0 and we are moving towards the right. In the right, what symbol you have? You have A here. So you have X here, you have Y here, you have B here and finally you have the blank symbol. I will also place the blank symbol here. Now we are in A. So again we are getting into Q0 comma A, which is the first transition. What happens? Q1 comma X to the right. So it is Q1. We are changing this as X and we are moving to the right. So what is here? Y is here. So Q1 comma Y. Do we have such transition here? Yes, it is here. It is not Y1, it is Q1 comma Y. What happens when state Q1 has Y here? It will just keep moving right. So here we have this X, here we have Y, here we have B. This particular transition just makes a movement to the next symbol. So what is the symbol here? It is B. Q1 comma B. We have already seen this transition. Q1 comma B will now transition to Q2 state, marking it as Y. So we will mark this as Y and we are moving to Q2 state. Now the head is moving towards the left. Left means you already have Y here. So we are getting back to this particular Y. We are in Q2 state and the symbol is Y. Do we have any transition for Q2 comma Y? Yes, it is there. Q2 transitions allow the machines to move back to the beginning of the string and look for the next unmatched A marked as X. So now we are again moving back to the left. So from here we are moving here to this particular X. What is this transition now? Q2 comma X. Do we have Q2 comma X? Yes, we have already seen it. Now we are changing to Q0 state here and we have to move towards the right. So taking this to be Q0 comma X, we are just moving towards the right. So now the transition will be Q0 comma Y. Do we have Q0 comma Y? Yes, it is here. Now we are moving to Q3 comma Y and we have to move in the right direction. So let's move to the right direction. Now the state will be Q3 comma Y. What transition is there in Q3 comma Y? This one. The state is Q3. There is no change to the Y symbol here and we are still moving to the right. We are already in the last symbol. So what is here after the last symbol? We have the blank symbol. So now we are moving towards this particular blank symbol in Q3 comma Y transition. Now we have Q3 state along with blank as the symbol. What is Q3 comma blank? We are here, and so we have reached the final state ultimately. So it is also processing AABB string. Regarding option 2, AB is also processed, AABB is also processed correctly. Option number 2 will be the right answer, and it is the official answer key that is provided. Let's go for option 3. What is n greater than 0? N greater than 0 is equivalent to n greater than or equal to 1. When you have n greater than 0, n's value will start from 1 and it goes on. When you have n greater than or equal to 1, there also n starts from 1 and it goes on like this. So they have typically taken this condition as the official answer key. But n greater than 0 is also right with respect to this particular language a power n, b power n. So I cannot rule out this option, but this can also be included in my opinion. So we are ruling out 1, but we are including 3 also as a possibility here. What about the fourth one? This condition here states that n will be greater than 1 where n is equal to 1 is excluded. This particular transition function is processing the string AB where n is equal to 1. This is excluded by option 4 because it is starting from AABB only. AABB is successfully processed, there is no doubt. But this language should include AB, which will not happen because n's value is greater than 1. So we can rule out fourth option also. Definitely 1 is not there, 4 is not there. We are going with option 2 as the right answer. But in my opinion, both these languages are same. This transition working will be effective only when you work it on your own instead of watching only in videos. Next question. Yacc is which of the following parsers? Yacc stands for yet another compiler. So this belongs to LALR parser. Option number 4 will be the right answer. I'll just give you a depiction here. This is how we create an input-output translator with Yacc. So Yacc specification is given with .y file. It passes through Yacc compiler and it changes to .c file. This .c file is passed through C compiler and we get .out file. When inputs are supplied from the user, this file gets executed and then the output is given. This input is given by the user and this output is what we see in the screen. Next question. Regarding the code optimization, choose the correct sequence. Algebraic simplification, use of mission idioms, redundant instruction elimination, flow of control optimization, improved target code. First we will understand what are these 5 statements. After understanding them, we will choose the correct sequence. Let's start with algebraic simplification. Simplifying algebraic expressions to reduce the complexity of computations. What does this include? Constant folding, strength reduction and simplifying expressions. What about use of mission idioms? Replacing general code patterns with mission specific instructions or idioms that are more efficient. This step is architecture specific and involves using instructions that are optimized for the target mission. What is redundant instruction elimination? This is removing unnecessary instructions that do not affect the program's outcome. This helps in reducing the code size and improving execution time. Common techniques include dead code elimination and common sub-expression elimination. If you want to know more about these terms, you can always refer to the reference book. Right now, I am just giving you the techniques that are used here. What about flow of control optimization? This is improving the flow of control in the code to make it more efficient. This includes techniques like loop unrolling, loop fusion and branch prediction. What is improved target code? Generating the final optimized mission code or target code that is ready for execution. This step involves register allocation, instruction scheduling and other low-level optimizations specific to the target architecture. Now, taking all these 5 steps, let's look at it in a general angle. Here we have something called final optimized mission code. So when you do code optimization process, finally you will have some output. That output is the target code that is ready for execution in the compiler phase. So E will definitely be the last step. Here you can find all the options are having E as the final step. Now we will check with A, B, C, D. You are going to simplify some expression, you are going to replace some pattern, you are going to remove some unnecessary instruction reducing the code size, and you are going to improve the flow of control. Actually, when you get 100 lines of code, you have to remove all the unnecessary instructions and you can reduce it to 80 lines of code. So reduction of code can happen in the first place. C will happen first in the sequence. So the sequence starts with C and ends with E. The only option that starts with C is option number 3. So we can go with option number 3 as the right answer. So redundant instruction elimination will be the first in the sequence. After that, you can optimize the flow of control. It means you can work with the loops and branches. So definitely C will be followed by D. The next work that you can do is simplify algebraic expression. Why do we actually simplify? To reduce the complexity of computation. So the next step will be A. We can replace general code patterns with mission specific instructions. Actually, B is going more target mission oriented and E is perfectly done for the target mission. If you find that the fourth step is going to be B, even here you have only one option with B in the fourth step. Just by reading the instruction, you can find this order initially and C to be the first one. So replacing general code pattern will be followed by step A. The correct order will be C, D, A, B, E. Next question. Which of the following CFG is in Chomsky normal form? All capital letters are variables, that is non-terminals, and lowercase are terminals. What is Chomsky normal form? CNF. CFL is context-free language and CFG is context-free grammar. Every non-empty CFL without epsilon has a grammar G in which all productions are in one of two simple forms. Either A derives BC, where A, B and C are each variables, or A derives small a, where capital A is a variable and small a is a terminal. This is what they have even mentioned in the question. Now let's check A. We have S derives A, B, C or AB. This production can be written as ABC and AB. Either you can have two variables in the right hand side or one terminal in the right hand side. Here you have three variables. So this is not in Chomsky normal form. Now let's get into B. X derives RT or TR. So this can be X derives RT and X derives TR. So there are only two variables here. What about the next production? T derives small t. This is also adhering to the rule. What about R derives xt and R derives R? So R is deriving two variables here and R is deriving one terminal here. All these productions go with the rules given in Chomsky normal form. So B is definitely in Chomsky normal form. Once you find that A is not in the list, you can rule out option 1. Once you find that B is included in the answer, you can rule out option 3. Now you have to check whether D is there or not. So initially we will work with D. We have M derives Mn, M derives MP. This is fine. What about N production? N derives Nm. This rule is saying it will have only one terminal. So this rule is actually violating CNF here. And then we have N derives N, which is okay, and P derives P is also okay. But this one is violating it. So D is not in the answer list. So from this you can also rule out option 4. Option number 2, B only will be the right answer. Now let's see what is wrong with C. P derives terminal, non-terminal. P P derives terminal, non-terminal. Q derives terminal, Q derives terminal. This is fine, but both these forms are wrong. This is perfectly wrong because they have told it should end up with two variables in the right side or one terminal in the right side. So this is also not in CNF. Next question. Match the list 1 with list 2. So we will see the Chomsky hierarchy now. Type 3 is regular grammar that is accepted by finite automata. Type 2 is context-free grammar accepted by push-down automata. Type 1 is context-sensitive grammar accepted by linear-bound automata. And type 0 is unrestricted grammar recognized by Turing machine. Recursively enumerable grammars generate all possible languages that can be recognized by a Turing machine. They have no restrictions on the form of their production rules. So recursively enumerable grammar will be type 0. A will be mapping to 4. The only option that maps A to 4 will be fourth option. So from this you can rule out the other 3. What about type 1 grammar? It is context sensitive grammar. One example is given in list 2 here. X derives y. Length of x is less than length of y, where x and y belong to variables and terminals together. This belongs to context sensitive grammars where the length of left hand side of a production rule must be less than or equal to the length of the right hand side. B is mapping to 3. What about type 2? Type 2 grammar is context free grammar. Context free grammar can be expressed in Chomsky normal form as we saw in the earlier question and Greback normal form. A Greback normal form grammar is a normal form for context free grammars. GNF is useful for converting CFG into a form that can be recognized by push-down automata. And regarding linear grammar, this is a type of context-free grammar where each production rule has at most one non-terminal on the right hand side. We are mapping C to 1. Greback normal form production rule will be A derives A alpha. Small a is a terminal followed by one or more variables is what we mention here as alpha. Somewhere they say this particular production rule structure is given by right linear grammar which is falling under regular language. So taking that point into consideration, we are mapping D to 2. A4, B3, C1, D2. Option number 4 will be the right answer. But if you take type 3 grammar, none of the options in list 2 are type 3 here. And whenever you take this particular hierarchy, whatever language is recognized here, that will be recognized by type 2 languages. So taking that into consideration also, you can map D to 2. Next question, match the list 1 with list 2. Conflict resolution in parsing often involves precedence rules to determine the order of operations. So we can map A to 2. A2 is available in 2 of the options. What about common subsequence? Finding common subsequences is related to optimization problems often visualized using direct acyclic graphs, that is DAGs. So we can map B to 4. B4 is available here. So we can rule out the other 3 options. Quadruples are a form of intermediate code representation used in 3 address code. So C will be mapping to 1. L attributed definitions are a type of syntax directed translation used in compiler design. So D will be mapping to 3. A2, B4, C1, D3. Option number 2 will be the right answer. Next question. From here we have a set of 5 questions. A machine is represented by states capital Q, input alphabet, transition function, initial state Q0 and final state F. The machine accepts all the strings over A, B which start and ended with any combination of all alphabets, and ABB works or lies as substring in all the strings to be accepted. It can either start with A or B and it can have any number of A's and B's. Similarly, it can have any number of A's and B's. But in between you should have the substring ABB is what this particular paragraph is telling us. Let's start working with the first question. For the above specified passage, which of the following represents the regular expression? A plus B means A or B. So let's start with A. What is closure symbol? It means zero occurrence can also be considered. Zero occurrence means sometimes this particular term can be totally eradicated. So we can have A as the starting, B as the starting and nothing as the starting, followed by AAB, followed by AAB, then only AAB can be taken. Are these three strings having ABB in between? No. So definitely one is not the answer. What about ABA? This will have a fixed string ABA and any combination of A and B can occur here. Closure is given, so definitely this will be the minimum string that is available for this language. So this expression is also not the right answer. What about this particular expression? Take out all the closure expression and only pick this alphabet here. We have B, B, A definitely, even when clean closure completely gives empty. BBA pattern is not mentioned in the passage. So 3 is also not in the answer. Here we have the string ABB. They say ABB works or lies as substring. So when this clean closure has zero occurrence, the minimum string will be ABB. Before ABB, in the starting, it will have any combination of all alphabets is what we can take it as A or B, the clean closure that comes in the starting as well as that comes in the ending. So this is any combination of A or B that we saw here in this particular format. So option number 4 will be the correct regular expression which represents the mission that is specified in the passage. Option number 4 will be the right answer. Next question. For the above specified passage, which of the following represent the grammar for the language accepted by the mission? So let's take the first option. S derives A, B, B. What does this production rule of A say? It has only A terminal along with epsilon. So this will have only A's and this B will have only B's. So it will start with A's, have the string ABB and then end with B's. What is the passage actually telling us? It should start and end with any combination of all alphabets. So the first option has an optional sequence of A's followed by the fixed string ABB followed by optional sequence of B's, which is not the one given in the passage. So one is ruled out. What about the second one? We have ABB string and then capital A. This A variable production will have A or B or epsilon. This actually satisfies the combination of all alphabet condition, but it is given only in the ending. What about the starting? We don't have anything. A fixed substring ABB followed by any combinations of A's and B's including none. So this is not talking about the starting and ending but only about the ending combination. So 2 is also ruled out. What about 3 here? We have A, B, then A. What is this A representing? It has A, it has B, it has epsilon. What about this A then? The same set of productions apply here also. So this represents the combination of all alphabet and this represents the combination of all alphabet along with the substring ABB here. So even when this A does not derive anything, ABB stands as it is. So the grammar given in option 3 is actually representing the grammar for the language given in the passage. Any combinations of A's and B's followed by the substring ABB followed by any combinations of A's and B's. This is perfectly matching So we can go with option number 3 as the right answer. What about option 4? It's just the same as option 2, but the variable is placed in the beginning. We have A, B, B. This A can be A, B or epsilon. What about the ending? There is no specification. Any combinations of A's and B's followed by fixed substring A, B, B. But they have not mentioned anything about the ending. So here the starting is missing and here the ending is missing. That's why we are ruling out option 4 also. Next question. For the above mentioned passage, which of the following is correct? So we have to find the automata of the language. Now let's take the first option. We have A, B, B string here, and this particular transition states that it has a combination of A and B. But there is no A and B combination in the ending part. So 1 will not be the right answer. Strings of A's and B's ending with ABB. It is not the right representation as given in the passage. What about the second one? Here we have ABB and then it ends with a combination of A and B. This will be the string of A's and B's starting with ABB. So this is also ruled out. What about third one? We have ABB here. It has A and B combination in the starting and A and B combination in the ending. So this will be strings of A's and B's in the starting and ending with ABB as substring. This is actually matching with the question, and so we are going with option number 3 as the right answer. Regarding fourth one, it is starting with AB combination, then it has the string A, B, B. Again we are given A and B combination. But why is option 4 ruled out? Here you can find this symbol to be the starting state and this symbol to be the final state. So initial will have this particular symbol and final will have double circle on the state. So this will be final. Regarding the fourth option, the initial state is 1 and the final state is also 1. When you make 1 to be the final state, you need not go for ABB string at all. Any combination of A and B will be more than enough for this particular machine to accept the string. If I say it is AB, this will be accepted. If I say only A's, it will be accepted because they have made the initial state as the final state. So this will not work for this particular passage. Strings of A's and B's in the starting and ending with ABB as substring is fine, but this accepts empty strings without ABB also, or it will accept any string that is without ABB also. So in that case we are ruling out option 4. Next question. For the above specified passage, which of the following is DFA for the language represented or accepted by the machine? What is DFA? Deterministic finite automata. For each state and input symbol, there is exactly one transition to a next state. In NFA, there need not be only one transition, there can be more than one transition. That is the basic difference. Now let's check for option 1. From state 1, for input A, we are in 1 itself. This self loop is 1. Again from 1 for input A, we are moving to state 2. So there are 2 transitions for the state with the same input symbol. This is not a DFA. Because for input A there are 2 next states 1 and 2. Just based on this we can conclude 1 is not the answer. What about 2? From 1 for A we go to 2. From 1 for B we stay in 1. From 2 for A we are staying in 2. From 2 for B we are going to 3. From 3 for B, we are going to 4. Regarding 4, we are ending up with the same state again. But does this automata represent the string that is given in the passage? We have to check that. It starts with B. There are many B's. then we have A, then we have many A's, then we have BB followed by A's and B's. This is not the string that they have defined in the passage. So 2 is also ruled out, though it is a DFA. Now let's check for the third one. From 1 for A we have 2. From 1 for B we have 1. Regarding 2, for A we have 2. For B we have 3. For 3, for A we have 2. We are just going this way back. And for B we have 4. What about 4? For A we have 5. For B we have 4. What about 5? We have A to state 5 again, then B to state 6. What about 6? For A we have 5. For B we have 4. Definitely this is a DFA. Let's check whether it is accepting the string given in the passage. This particular part is having combination of A's and B's together. 3 to 2, 2 to 3, 3 to 4 can give ABB, or 2 to 2, 2 to 3 and 3 to 4 will also give ABB. 4, 5, 6 will be any number of B's and A's together. Strings of A's and B's in the starting and in the ending with ABB as substring. This one is a DFA, as well as it is accepting the strings given in the passage. Let's check the fourth one. From 1 we have A and B transition. From 2 we have A and B transition. From 3 we have A and B transition. From 4 A and B. From 5 we have A and B. From 6 we have only B. So now we have to check for ABB string pattern. String of A's followed by B in the starting, followed by ABB string. Again we have string of B's in the ending. If you take this particular part, you will have strings of A's, but only one B is given in the transition here. So here it is string of B's and here it is string of A's. But the combination should have A's and B's together. So 4 is also ruled out. So option number 3 will be the right answer. This is the DFA for the language represented by the mission given in the passage. The final question. Which of the following represented the minimum state DFA for the above specified passage? This is the DFA that we have got from the previous question. What is minimal state DFA? It has the smallest possible number of states while still recognizing the same language as the original DFA. So the original DFA had 6 states. Minimal state DFA will have smallest possible number of states. So based on this particular DFA, we have to make sure there are reduced number of states. First let's check option 1. From 1 you have 2 transitions with input symbol A. This is not a DFA. In state 1 there are 2 transitions for A. Only when it is a DFA we can check whether it is minimum state DFA. So option 1 is ruled out. What about option 2? This state 2 has 2 transitions for the same input symbol A. This is also not a DFA. In state 2 there are 2 transitions for A. So we will even rule out option 2. What about option 3? For 6 you have 2 transitions with A here. This is not a DFA. In state 6 there are 2 transitions for A. So we can rule out even option 3. What about option 4? Here also this is violating the DFA rule for the same input symbol. This is also not a DFA. In state 1 there are 2 transitions for A. So we are ruling out even option 4. All the representations given here are NFA. Only when it is a DFA we can check whether it is minimal state or not. Since none of the options are correct, this question has been dropped in the official answer key. With this we are completing Unit 8 solutions.